All right, you ready? Close enough to ready? Is the temperature in here better?
Yes.
Better? Is it getting on the warm side? Okay. All right. So the last 2 or 3 topics I have in Chapter 2 before we move on to Chapter 7 is just the periodic table and the mole. So we'll cover those 2 today, then we'll get started on Chapter 7. You have the final Chapter 2 homework due tonight on mastering, and we'll do a group quiz today. Then looking ahead to Monday, we'll do an individual quiz. And do not forget, if you have lab next week, you will have to have your lab manual with you in lab. As long as your lab notebook and goggles and whatnot, but have all those things purchased for lab next week. All right, next let's talk about the last few things in Chapter 2. So the periodic table. So when the periodic table was constructed by Mendeleev, he constructed it based on the elements known at the time, and he noticed that as he was putting it together, certain elements had similar properties. And he developed what's called the periodic law. Periodic law states that when elements are arranged in order of increasing mass, certain sets of properties occur periodically. So by setting up the periodic table in this manner, we see that elements in a shared column all have properties that are similar to each other. So we're elements in one column. They're going to share properties. All right, so the names of some of these groupings are metals, nonmetals. And metalloids. So metals are things, they're elements that tend to lose electrons. If you lose an electron, what does that make your new charge? Positive. So what would I call those guys? A cation or anion? Right? So metals tend to be positively charged or cations. That means nonmetals tend to be negatively charged or anions. And the metalloids can gain or lose electrons. There is no great rule about how we define they gain or lose. So, looking at our periodic table, you can see that they're all kind of arranged in columns. If we're looking at left to right, column 1 and 2, so the columns that have like lithium, sodium, magnesium, calcium, those guys are metals. If we look over to the other side, and we look at column, like just about all of 16 and most of 17, those guys are nonmetals. It's actually where this big blue solid line is. So you can see it's like a triangle. That's like boron, silicon, arsenic, tellurium, acetine, and up that triangle right there is nonmetals. Column 17 and over 2. Those are the nonmetals. So if I'm looking at my periodic table, these two are metals. That kind of triangle slice are nonmetals. And everybody in the middle here is considered a metalloid. What's the name of this column over here on the very, very end? Right, those are the noble gases. They don't fall into any of these other categories. So this column so there's some special names, right? So the noble gases have their own name, right? Column 18, we call it the noble gases. Column 1 has a special name. We call that the alkali metal. Alkali metal column. Column 2, we call the alkaline earth metals. And the only other column that has a special name is 17, which are our halogens. And they typically have special names as a column because they have unique and interesting chemistry that goes on with them. So column 1 and 2 are super reactive cations. Column 17, the halogens, are super reactive anions, noble gases, right, or the unreactive gases. And so they have special names because they have special properties, which we will get to why they're so special. Let's see. Okay, atomic masses. So, we talked about this a little bit on Wednesday, right? We had magnesium and it had 3 different isotopes, each of which had a different mass. But then we look at the periodic table, the mass given is 24.3, which means we know that the mass is most likely, more often than not, 24 AMUs. So let's take a look at magnesium again and see why that is. All right, so the periodic table shows magnesium to have a mass of 24.31. I'm rounding a little bit. Atomic mass units. And we also knew that magnesium had 3 different isotopes. All right, we got those 3 isotopes that we talked about the other day. What's the difference between all 3 of these isotopes? Yeah, it's the number of neutrons, right? I had 12 neutrons, 13, and 14 different neutrons. Okay. So if I know, if you would like to know how we solve this, I can tell you later. But we can determine that 79% of the time it's isotope number 1, 10% of the time is isotope number 2, and 11% of the time is isotope number 3. So, an atomic mass is a weighted average of these 3 isotopes, which means we can determine the overall mass by using a weighted average method. So, you will need your calculator out. You can find it, or something to calculate with. All right, so if you think of a weighted average, you should be thinking like maybe you're grading here, right? So if the exam is worth 15%, and the quiz is worth 10%, and the labs are worth 12%, whatever it is, right? That's a weighted average. It means whatever average you had on your quizzes, multiply that times 0.12. And whatever you got in your exam, multiply that by 0.15, right? That's a weighted average. We're going to do the same thing for this. I want to figure out the overall mass, and I know what the percentage is. So we're going to use math to prove that this is correct, and then we'll do another problem. So I'm going to look at isotope number 1. Its overall mass is 24. How do I turn 79% into a decimal? Right, 0.79. So that tells me 79% of the time it weighs 24. I'm going to add that to the next mass, which is 25. Well, what do I multiply that by? I heard it, right? 0.1. And I ran out of space on my paper. I'll write real small. Then the last mass is 26. And I multiply that by 0.11. So everybody take a second. Make sure I did my math right. You guys have very quiet calculators. How many significant figures do I get in this? Oh. How many significant figures, right, because it's going to be by parts, like in lab. So how many significant figures do I get in this section? 2. How many significant figures do I get in this section? Okay. What about this section? 2. But now I'm going to add them together. So what rule do I use now? I use it by decimal places. So how many decimal places will I be able to use? 2. All right, so that seems pretty straightforward. So let's do another one. Let's do this one. All right, so let's say I'm looking at lithium. And let's say if lithium was shown to have 92.58% of the time a mass of 7.016 and 7.42% of the time .015 atomic mass units. What is the correct average mass for lithium? So before you start looking at the percentages and the masses, what should it be close to? 7, right? Because 93% of the time it weighs 7, and about 7% of the time it weighs 6. So we would expect an answer close to 7. So how do I set up the first multiplication? What two things do I multiply together? I hear 7. Yeah, okay, we'll do that. Then what do I multiply that by? How do I turn my percentage into a decimal? Right, do this. Okay, so then there's my other mass. Then how do I turn the other one into a decimal? All right, so then let's see here. 1.06 times 90.9258. 4. Okay, so right, I had 4 significant figures in each of these. So my answer is in 4. 4. Oh, 3. I had too many decimals. 4. There we go. So 4, but 3. So then I get 3 here. So now I'm going to add them. So what rule governs my adding? Number of decimal places. How many decimal places do I get? 3, which it happens to be in 3 already. So that's good. Let's double check the periodic table. Spot on. Very good. The answer on the board is 6.941. Yeah.
Right. What if it gave you like the atomic mass and like
like in the homework.
Yeah.
Yes.
That's
Yes.
cool.
Yeah. All right. Let's do that one. Let's see if I have one of those. Let's see if I can come up with one real quick. Here we go. All right, so let's say I have silver and I'm on the periodic table and I see silver has an atomic mass of 107.868. I know 48.16% of the silver has a mass of 108.905. What is the mass of the other isotope? So, thinking through it, we're going to set it up very similar to the problem that we just did, right? So I'm going to have right, I know that's right, that's the percentage. I'm going to turn that into a decimal point. Oop, that should be a 0. 8. Right, those are the two pieces of information we definitely know. What do we know about these other two parentheses? Right, because I have percentage mass. Do I know either the percentage or the mass?
You get the percentage.
I know the percentage. How do I figure out what the percentage is? Subtract it from 100, or in a decimal point, subtract it from 1. So 100 minus 48.16. And then this is the thing I'm looking for, right? That's the mass I don't know. Call that X. So then that's going to be equal to the mass they gave us, 107.868. Does that solve it?
Well, in the homework, they don't give us either of the percentages.
Oh! Let's say I didn't give you this percentage. I'll let you guys tell that on your own. Let's say I have, like a random, I don't know the percentages of cobalt. We'll pretend. So, element, pick a random letter, we'll do. That's not a real element. I'm good. If it's not a real element, it can't be wrong. So we'll just do this. So I have element this. We'll say mass of all right, so I know that's the mass. Did they give you the two isotope weights?
Yeah.
Okay,
Yeah, the percentages was the only thing I left out.
gotcha. All right, so let's say I have two masses, and I know the final thing. So we'll set it up like we have up here. So here's my final mass. Okay, so I know for sure into two of these parentheses I put the masses. How are the two percentages related? Right, they all add up to 100, or in decimal point form, right, they add up to 1. So if I call this one X, how do I know what this value is if they add up to 1? It has to be 1 minus X. So now you're going to want to do some simplification and some algebra. Right, you're going to want to multiply this out. So you'll have 53.44 and minus X times that. Of my new terms, what can I put together? The things that have X's together, right? So So let's see, 56.497 plus, minus 53.544. All right, how do I now get the thing with the x on a side of the equation by itself? Subtract, right? So from both sides, I'm going to subtract that 53. So now I'm going to do 54.694 minus 53.544. All right, we're like one step from the end. Now what? Divide. Do I divide 1.15 by 2 or 2 by 1? So let's see what's that turn out to be. 2.9, 3. So what percentage is that? So then what would be the other percent? Like 60-ish%, right? So the other one has to be like 61.1%. Good, everybody feel fairly confident about your algebra? Yeah.
Could you add the 53.4 and then divide?
Could I add these two together?
No.
Yeah.
The other two.
Oh yeah, I could have added the other two. Like I could have skipped a step.
Like not, yeah, add the 2.953.
Yeah, I could have done that. Yeah, that was okay too. All right, good. Okay. In that case, let's finish up the last thing in chapter 2. Which is the mole. Alright, so I'm only going to spend a minute on this because I think most people have at least talked about the mole in some version or form, right? So often we want to count up the number of atoms, but since atoms are so small, we have to group them into a larger collection in order to count them correctly. So we use this counting amount called the mole, where the mole means any amount of material that contains 6.022 times 10 to the 23rd things. Anyone know the other name for that number? Right, that's Avogadro's number. Avogadro's number. All right, so I could have a mole of just about anything. Mole doesn't refer necessarily just to chemistry. I could have a mole of donuts, which sounds amazing right about now because I haven't had breakfast. A mole of donuts, right, would be 6.022 times 10 to the 23rd donuts. That would be pretty awesome. Or shoes. I could have that many shoes. I'd need a bigger closet. All right, 6.022 times 10 to the 23rd shoes. Or a bunch of pennies, right? I could have 6.022 times 10 to the 23rd pennies, which would weigh a lot. But more often we use this in terms of talking about chemicals. Right, so a mole of water would be that many water molecules. So the value of a mole is equal to the number of atoms in 12 grams of carbon. which means that 12 grams of carbon is equal to 1 mole of carbon, which is equal to 6.022 times 10 to the 23rd carbon atoms. Which means I now have conversion factors, right? I have two different units that refer to the same thing. So I can go from grams to moles, moles to atoms, atoms to grams. I now can convert between one unit to another. So I now have conversion factors. I can convert between moles to atoms and back and forth. So let me see if I can come up with a clever example. Let's say I have let's say I have 10 moles of calcium. Let's say if I have 10 moles of calcium, how many atoms do I have? So using our method of unit conversion, right, I'm going to start off with the units that are given. What units do I want to end up in based on this question? I want to end up in atoms. I guess I hid my conversion factor. So I have atoms over here, and I got moles, which I can write as this. Right, that's the same way, changing that equal sign to a division sign. So how do I use this conversion factor to get atoms by itself? Do I put atoms on the top or atoms on the bottom? Atoms on the top, that way I get atoms to my final unit, my moles cancel out. I didn't pick a very tricky problem, did I? 6.022 times 10 to the 22nd. Oh, wrong way. Fourth. Okay, but not a particularly interesting question. Let's see if I can come up with something more clever. We'll do it in terms of mass. Let's say I have mass. So I think this is the last slide in your PowerPoint packet. Let's say I'm now concerned about mass. Right? Because while it's awesome to know that I have a quadrillion atoms, it's not super useful in terms of like measuring. It's more interesting to know the mass of that many atoms. So, the mass of 1 mole of atoms is equal to its atomic mass. Where do I find the atomic mass? On the periodic table, right? The little numbers on the bottom. How handy is that? So let's say I have, what element do we want to pick? Let's pick, well, I never picked vanadium. Let's do vanadium. Number 23. I have I have 120.4 grams of vanadium. I want to go from grams all the way down to atoms. Okay. So we're going to start with the unit that we're given. And I want to go from grams to atoms, but I can't go there directly, right? I have to go through a step in the middle. Using my definition up here that the mass of 1 mole is equal to its atomic mass. So side note. If we go ahead and look at the atomic mass of vanadium, which I know is tiny, you can't read it from here. It's 50.9415. And we've been talking about that in terms of, right, AMUs. That is correct. But we can also call it grams per 1 mole. Those units are interchangeable. Atomic mass units really means grams of vanadium per 1 mole of vanadium. So, can I use my new fancy conversion factor to get out of grams into something more useful? Obviously, yes. Otherwise, I wouldn't have been asking this question. All right. So, here I have my grams per mole. Do I put the 50 on the top of the fraction or on the bottom of the fraction? Put it on the bottom. All right. Am I in atoms yet? No. How do I use my snazzy Avogadro's number to get from moles to atoms? What stuff do I put a 1 on top, or do I put a 6.022 times 10 to the 23rd on top? The 6, okay. All right, since I just made up this problem, I don't actually know what the answer is. 120.4 divided by 50. 9.0 times 6.022 third. How many significant figures do I get? 4, right? Because it's just a multiplication problem. So I had 4 times 6 times 4, so I only get 4 significant figures. And then what units am I left in? Atoms. Okay, we're going to do a lot more conversion factors as we come up. I guess I will save Chapter 7 for Monday. Sad. I want to make sure you guys have enough time to do your group quiz. So if you guys want to go ahead and move yourself into your groups. It's going to be the same as last time, that everybody gets one, but I only need one turned in per group. And everybody's name has to be on it.
I got you, Brenda. You're well.
Are you going to keep me out of the group?
I don't know. I don't know if I'll do it.
And you will need at least one calculator per group.
I've already told them. Because it gets another question wrong. What? You have this one, all you.
Oh, just kidding. I'm sorry. Sure, absolutely.